In this video, we're going to continue with CC7 because CC7 is going to be on paper 1 and paper 2, and we're specifically going to look at allotropes of carbon. First thing we're going to do is look at what an allotrope is, and an allotrope is just different structural forms of the same element. Because we're looking at allotropes of carbon, we are going to look at different structural forms of the elements. Carbon is a non-metal, so it is in group 4 of the periodic table. It is a non-metal, and because we're looking at different structural forms of carbon, the only element we're going to look at is carbon. So it's going to be bonding to itself. All the bonding that we look at in this video is just going to be carbon bonding to another carbon atom. Because it's non-metal bonding with a non-metal, carbon is going to form covalent bonds with itself. So everything we look at in today's video is going to be covalent bonding because it's carbon and non-metal bonding with another carbon atom, also a non-metal. We've already looked at covalent bonding in previous videos, and we've looked at covalent bonding to form simple molecules. However, there is another type of covalent bonding. There is also giant covalent. In each case, it's covalent bonding, so it's non-metal atoms bonding with other non-metal atoms. But when you form a simple molecule, as we've seen before, okay, you've got non-metal, so it's forming covalent bonds, but you've got a known number of atoms. And by that, I mean I know exactly how many atoms. Example of a simple molecule, I've got 1 carbon, I've got 2 oxygens. H2O is a simple molecule, 2 hydrogens, 1 oxygen. I know exactly how many atoms I've got. I can write a formula, and they are relatively small. When we're looking at allotropes of carbon, as I said before, you've only got carbon bonding to other carbons. So CO2, yes, it's a simple molecule, but it's not an allotrope of carbon because you've got oxygen in there. And to be an allotrope of carbon, I should only have carbon atoms. If I'm looking at an allotrope of carbon that is a simple molecule, then I'm going to look at Buckminster fullerene, which is a spherical fullerene. So fullerenes are hollow structures. You can see from this diagram here that I've got a sphere that is hollow on the inside. So because it's hollow, I'm going to call it a fullerene, and I'm going to call it a spherical fullerene because it's spherical in shape. If you're asked to describe the shape of this, it is incorrect to say circular. It's a 3D structure. You have to describe it as spherical. We said to be a simple molecule, there had to be a known number of atoms, and they all had to be non-metals. Each of these black dots represents a carbon atom. Carbon is a non-metal, so all of the bonds that you can see here are covalent bonds. In total, I've got 60 carbon atoms. Because I know exactly how many atoms I've got, because I can write a formula, it counts as a simple molecule. C60 will be the formula for this Buckminster fullerene. C60 is obviously a lot bigger than something like H2O or CO2, but it is still relatively small. And because I can write a formula, I can say that it is a simple molecule. So sorry, fullerenes are just hollow structures in general. This specific fullerene with 60 carbons is called Buckminster fullerene, but there are lots of other different fullerenes that have a similar shape, but just have a different number of carbons. There is also another type of covalent structure, and this is called giant covalent. Again, because it's covalent, it only contains non-metals, and all of the bonds are going to be covalent. However, with simple molecules where you had a known number of atoms, with giant covalent you have an unknown number of atoms. And the reason you don't know exactly how many atoms are there is because it's a giant structure, it's huge, and you've got millions or even billions of atoms. You've got so many atoms that you can't write a definite chemical formula. So over here, I could write the formula for my spherical fullerene was C60. But when we look at all of the examples of giant covalent, you'll see that I never write a chemical formula for them because there are so many atoms. I don't know exactly how many I've got. It depends on the size of that piece of that structure. It's going to vary, and I'm not going to be able to write a chemical formula. There are a couple of different giant covalent structures that you need to know. Remember, these are all allotropes of carbon, so every structure that we look at is just carbon bonding to other carbon atoms. There's no other element involved in this entire video. So the first giant covalent structure we're going to look at is diamond, and I'm going to put a picture of diamond for you, okay? So each black dot here, as I said, represents a carbon atom, and you'll see that each carbon atom can form 1, 2, 3, 4 bonds to other carbon atoms. Again, because these are non-metals, all of these bonds are covalent, and these covalent bonds are very strong. Now, this is a giant structure. What's shown here is only a really, really small portion of diamond, okay? In reality, this would continue in every single direction, and you would have billions of carbon atoms, but for drawing sakes, you're not going to draw out billions of atoms, you're just going to draw a small portion. You can see that because each carbon atom forms 4 bonds, the carbon atoms are arranged in this 3D structure. All of these covalent bonds are incredibly strong because you've got lots of really, really strong bonds holding these atoms together. Diamond is going to have a really, really high melting point because it would take a lot of energy to break down all of these really, really strong covalent bonds. Because each of these carbons are atoms, okay? Atoms are not charged. That means diamond doesn't have any charged particles, and therefore it's not going to conduct electricity. So I've just jotted those points down below. So it's only got carbon. Each carbon atom forms 4 bonds. Remember, carbon's in group 4. It's got 4 electrons in its outer shell, so it can form a total of 4 bonds. All of the bonds it forms are covalent bonds, which are incredibly strong because you've got lots of high melting and boiling point, and it is not going to conduct electricity because you do not have free moving charged particles. If you were asked for 2 or 3 marks about diamond, I've got some typical diamond questions here. Okay, so it says diamond is a giant covalent substance. What would you expect its properties to be? Giant covalents typically high melting and boiling points, so they're solid at room temperature and they can't conduct electricity. If you were asked to explain those properties, why is diamond solid? Why does it have a high melting point? You would say that it's got a giant covalent structure, or it's a giant covalent substance, that you've got lots of strong covalent bonds holding those atoms together. Because you've got strong covalent bonds, a lot of energy is going to be required to break those bonds, which means the melting point is high. If a lot of energy is required, that means a lot of heat is required. That means high temperature, so melting point is going to be very, very high. If you're asked why does diamond not conduct electricity, you'll say there are no charged particles. There are no, I'm going to say, free-moving charged particles. Do you specify they don't have free-moving charged particles? Therefore, you've got nothing to carry current. Okay, so that would be diamond. Another example of a giant covalent allotrope of carbon is going to be graphene. So like what we saw before, each of these black dots is representing a carbon atom, which means all of these bonds are covalent bonds. You've got lots of strong covalent bonds. But in diamond, each carbon atom formed 4 bonds and it formed a 3D structure. In graphene, each carbon atom is only forming 3 bonds, so it's just forming a sheet. Because all of these bonds are covalent, which are strong, like diamond, graphene is going to have a high melting and boiling point because it would take lots of energy to break all of those covalent bonds. However, graphene does have a property that diamond does not. Because each carbon atom is only forming 3 bonds, but it has 4 electrons in its outer shell, each carbon atom in graphene is going to have 1 spare electron that is not involved in bonding. These spare electrons are then free to move throughout the structure. Remember, electrons are charged. They have a negative charge. And if you've got electrons that can move freely, then you have free moving charged particles. That means graphene is able to conduct electricity. Okay, so diamond cannot conduct electricity, but graphene can. The reason that you've got this difference is because graphene has delocalized electrons, and delocalized electrons can carry current. So if you were asked, just put this underneath, why does graphene conduct electricity? You will say that each carbon is only bonded to 3 other carbons. That means it's got delocalized electrons, and those delocalized electrons can carry current throughout the structure. Other than that, your answer for graphene would be the same as your answer for carbon. So if you were asked why graphene was a solid at room temperature, you would say giant covalent, strong covalent bonds, lots of energy required, so that melting point is going to be high. So for your melting or boiling point, your answer for graphene would be the same as diamond, but for conducting electricity, you need to mention the fact that it's only got 3 bonds, therefore has delocalized electrons, therefore can carry current. Graphene is one single layer. Graphite is just multiple layers of graphene stacked on top of each other. Because graphite is just multiple layers of graphene, the properties are going to be the same. It's going to have a high melting point because you've got lots of strong covalent bonds between those carbon atoms. It's going to be able to conduct electricity because each carbon atom only forms 3 bonds. Therefore, you've got delocalized electrons. So the properties that you learn for graphene are going to be the same as what you learn for graphite because graphite is just multiple layers of graphene. However, there's one additional property that you can say for graphite. Because it is stacked up in layers, the forces between each layers are weak. And that means that even though the layer itself is very strong, the attraction between the layers, because that is weak, it means that these layers can slide over one another. Because these layers can slide over each other, yes, graphite is still a solid, but it's actually a slippery solid. It's what you find inside your pencils. So you know from using your pencil that your pencil can glide across the page because it's quite slippery. You'll also know that your pencils are quite easy to break. So yes, it is a solid, and yes, it has a high melting point. It would be difficult to turn it into a liquid, what's inside your pencil. But because you've got weak forces between those layers, you've got a slippery solid, and you've got a solid that can be easily broken. That's in contrast to diamond. In diamond, you don't have any weak forces at all. All you've got in diamond is just really, really strong covalent bonds. So diamond is incredibly hard, incredibly strong. You use diamond at the end of drill tips because it can drill through anything. It's so hard and it's so strong. But graphite, even though the covalent bonds are incredibly strong, which gives it a high melting point, because you do have weak forces between the layers, it's not a strong, hard solid like diamond. It is a soft, slippery solid. So if you were asked about graphite specifically, they could ask you, okay, number 1, why can graphite conduct electricity? Just like graphene, you would say bonded to 3 other carbon atoms, delocalized electrons, can carry current. If you were asked, giant covalent structures are typically hard. Why is graphite soft and slippery? So diamond we saw was really hard. Why is graphite soft and slippery? You will say that you've got layers, and those layers are only weakly attracted to each other, so those layers can slide, okay? That's why it's a soft and slippery solid, okay? But they could still ask you, why does graphite have a high melting point? And if you're asked why graphite has a high melting point, it's going to be exactly the same as what you said for diamond. It's giant covalent, lots of strong covalent bonds, therefore you need lots of energy to overcome. It's going to have a high melting point, okay? So some of those answers are going to be exactly the same, but then for the conducting electricity and the soft and slippery solid, the answer for graphite is going to be different from your answer to diamond. One more allotrope we need to look at, and that's if you take a graphene sheet and you roll it up into a tube, okay? So because you're just taking a sheet and rolling it up into a tube, or a carbon nanotube as we call it, the properties of your carbon nanotube are going to be exactly the same as your properties of graphene, okay? You've just taken your graphene, rolled it up into a sheet. So again, I can say that your carbon nanotube has a high melting boiling point because of those strong covalent bonds. I can say that it can conduct electricity because you've only got 3 bonds for each carbon atom. It's got delocalized electrons. So those your carbon nanotube, just like graphene and diamond and graphite, it is giant covalent. This is only a small portion of a carbon nanotube. In reality, you'd have billions of carbon atoms. So in reality, it would keep going in both directions. You'd have billions of carbon atoms, and it is a giant covalent structure. There's another word that you can use as well for carbon nanotube. I said before that a fullerene was a substance with a hollow structure. So we saw spherical fullerenes over here. This carbon nanotube, because it's got a hollow structure, it can also be described as a fullerene. Okay, so just to clarify, fullerenes, they are hollow structures. We saw a spherical fullerene. Now we've got a fullerene in a tube. My spherical fullerene had a known number of atoms. I had 60. That means my spherical fullerene is a simple molecule. However, my carbon nanotube does not have a known number of atoms, so my carbon nanotube fullerene is going to be giant covalent. If we just look at the following table, it will summarize. So your allotropes of carbon, you've got 5 of them. You've got spherical fullerenes. They count as being simple molecules. Again, they're molecules because I know exactly how many atoms are there. There are 60 in total. Your giant covalent structures, you've got diamond, you've got graphene, which is a single layer, graphite, which is when you've got multiple layers, and a carbon nanotube, which is when you take that layer of graphene and roll it into a tube. In graphene, graphite, and carbon nanotubes, each carbon atom forms 3 bonds. Therefore, they all have delocalized electrons. Therefore, they all conduct electricity. With diamond, each carbon atom forms 4 bonds. Therefore, they do not have any free moving charged particles. They do not conduct electricity. All of your giant covalent structures all have high melting points because of those strong covalent bonds. The additional property you need to know is that for graphite, because it is arranged in layers with weak forces between layers, it is soft and slippery. So that's an additional property you need to know. Just be mindful when I'm talking about the 3 bonds and 4 bonds, okay? What students often write is, in graphite, there are only 3 bonds, okay? That's very, very wrong. Okay, graphite is a giant covalent structure. You've got billions of bonds. So when you're talking about the 3 bonds, you have to say each carbon atom only. It is very, very wrong to say that there are only 4 bonds in diamond. There are billions of bonds in diamond. What you would need to say is each carbon atom forms 4 bonds. Okay, so just make sure you're using the right terminology there. If we look across at our spherical fullerenes, they are simple molecules, so have the properties of simple molecules. If you remember simple molecules, we saw that you had weak intermolecular forces between molecules. Spherical fullerenes are the same. You've got weak intermolecular forces between molecules. That means you're going to have a relatively low melting and boiling point in your spherical fullerenes. Spherical fullerenes are also very poor conductors of electricity. If we look at my spherical fullerene again, they are very poor conductors of electricity. Yes, each carbon only forms 3 bonds. So yes, you've got delocalized electrons, but those delocalized electrons in the sphere, whereas if you had a fullerene, you would have lots and lots and lots of different spheres, and the electricity cannot move from one sphere to another. Okay, so you can carry electricity across the sphere, but to be a good conductor of electricity, you would need the electricity or that current to get from one sphere to the next to the next. So yes, they have delocalized electrons, but you can't carry electricity from one sphere to the next. That makes them poor conductors of electricity overall. The other thing that they can ask you about fullerenes, I think I have this written for you here. I do. So I have all of this written for spherical fullerenes. So I have each carbon bond so has delocalized electrons, but a poor conductor of electricity, as current can only pass within the molecule, so within that sphere, and not from one molecule to another. So if you look at this picture here, if you had your Buckminster fullerene, you'd have lots and lots and lots of these molecules. And to be a good conductor of electricity, the electricity would need to be able to pass from one side to the other. The electricity can stay within the sphere, but it cannot move from one to the next. That makes it a poor conductor of electricity overall. And the other property of fullerenes that I didn't mention is, again, they are actually soft and slippery. They can be used as lubricants because they are soft and slippery. And just like we had with our graphite, where I said the layers can slide because there are weak forces between layers, here you can say you've got weak forces between your spheres, and because they're spheres, instead of describing them sliding, I'm going to describe them as rolling. Weak forces between the spheres, so the spheres can roll. So here, why are fullerenes used as lubricants? Weak forces, the spheres can roll over each other, it makes them soft and slippery. Why do fullerenes have low melting points? Weak intermolecular forces require little energy to overcome. Okay, there are lots of practice questions in your booklets on this. I'm just going to go to one exam question. I'll just do one exam question with you. This is one that came up 2 years ago. Graphene sheet, they rolled it up into a carbon nanotube, and what they wanted to know is, why are carbon nanotubes strong? To get your 3 marks on this, you will need to say that a carbon nanotube is giant covalent. Okay, so that's the structure, giant covalent. Because it's giant covalent, you have got lots of strong covalent bonds. So you get a mark for saying giant covalent. You get a mark for saying that those covalent bonds are very strong. And then anytime you're asked about strength or melting point or anything like that, you need to talk about energy. Because you've got lots of strong covalent bonds, you would need lots of energy to overcome those strong covalent bonds. Okay, just one more that we'll look at together. They've given you a row. So they've given you a table that has properties of carbon, fluorine, and tetrafluoromethane. So you've just got carbon, you've got fluorine, and then you've got tetrafluoromethane, which is a carbon bonded to 4 fluorines, CF4. And I want to know which row describes the properties. Okay, we've just looked at carbon. Okay, and we've seen that carbon has high melting and boiling points because of all of those strong covalent bonds that it forms. Okay. On the other hand, over here, tetrafluoromethane, carbon's a non-metal, fluorine's a non-metal, so you're going to have covalent bonds, but I've got a known number of atoms, so it's going to be a simple molecule. Because it's a simple molecule, you've got weak intermolecular forces, I would expect the melting point of tetrafluoromethane to be incredibly low. So what I want to look for is I want a really high melting point over here for carbon, and I want a really low melting point over here for tetrafluoromethane. So it's not going to be 120, that's too low for carbon. Minus 184, way too low. Minus 220, way too low. 3,500, that sounds about right for carbon. Coming over here to tetrafluoromethane, I want something low, so minus 184 would suit. If I look at what I've got in the middle, I've got fluorine. Fluorine, again, is a non-metal. It's diatomic, so it's F2. So just like the molecule, meaning I would also expect it to have a low melting point, and therefore my answer is going to be A. In a later video, I'm going to do more exam questions on structure and bonding. So please do watch that to make sure you've got good exam technique.